And we're back. Welcome back, guys. Let's go ahead and look at an example. Now, when you get to worksheets, tests, quizzes, I'm going to give you fun things like this. And what you have to do is at a given x value, you have to figure out, is it continuous, differentiable, is it neither of the two, or maybe it's both of the two? Okay, so this is fun stuff. So if I look at x equals negative 2.5, so from the origin, go to the right 2.5, so we're looking right here. Can you draw a tangent line there? Heck yeah, that's a curve. I can touch to the point. Can you trace over that value without picking up the pencil? Absolutely. So this is both differentiable and it's continuous. Yay! Okay, negative 1. If I go to the left 1, oh boy, oh boy, oh boy. Can I draw a tangent line there? Well, no, you can't, because look at, there's this big jump, and would it be there, would it be there, and that's a point, and yeah, that doesn't work. Can I trace over negative 1 without picking up the pencil? Well, no, because if I'm coming here, then I have to jump up to here. If I'm coming from this way, I have to jump there. So this is a big wah, wah, wah. It's neither. Okay, how about 0? Darn it, same thing. Look at this. That's at 0. If I'm trying to do a tangent line, well, that doesn't even, there's a hole there. And you can't put a tangent line on a point that doesn't exist. Okay, if I'm trying to trace going to 0, I'd have to jump over here. Here I'd go, and I'd have to jump. So again, wah, wah, wah. Neither. Okay, x equals 2. So here is x equals 2. I cannot draw a tangent line because it's a point. Remember, a tangent line has to be at a curve. So I do not have a tangent line, but look at this. Guess this. I can go ahead and trace from this way and go from this way. I don't have to pick up the pencil. So this is continuous. It's not differentiable because of that darn point, but it's continuous. You can trace over it without picking up your pencil. Negative 0.25. So if I go to the left, a quarter of a unit. Oh, I got that. Can I draw a tangent line? Heck yeah. Can I trace over that? Absolutely. So it's both. Yay! Okay. I really like this stuff. You will have this on tests and quizzes. Okay, just kind of be prepared for that. As you're doing the book assignments, when you get things like this, go ahead and refer back to those graphs because you can see what is differentiable, what is not, as well as reasoning behind it. Okay. You might be able to go to Desmos, okay? However, these two, I think that we can totally do this without even going to Desmos. If I have f of x equals x squared, there's the parent function right there. Could you find a tangent line at x equals 0? It's right there. Heck yeah, you can go ahead. Right here, remember, this would be a minimum point. If you have a tangent line at a maximum or a minimum, that's where your slope is 0 because it's a horizontal line. Can you trace over 0? Absolutely you can. So this is both continuous and differentiable. Now this was one of my examples, 1 over x squared. So here is what that graph looks like. At x equals 0, you cannot draw a tangent line because it's an asymptote. You can't go ahead and trace over it because there's a big space there, again, because it's an asymptote. So when I look at that one is neither, okay? Now the next thing, if you want to know if piecewise functions, if they are continuous or differentiable, it's two different processes. If it's continuous, that means that they're connected. So at whatever the x value is, to see if it's continuous, you fill it into the original value. If you get the same y value, what that means is when you graph those two things, they will be connected, so you would not have to pick up the pencil. So if I go ahead and put a 3 into the top function, 3 squared equals 9. If I put a 3 into the bottom function, 2 times 3 plus 3 equals 9. When I filled them into the original, they matched. That means it's continuous. Now remember, differentiable, that is based off of the derivative. So what you have to do is find each derivative. So this is 2x, and this is 2. Now fill in the 3. If you can fill the 3 into the derivatives and they match, then it's differentiable. If they don't match, then it's not. So I can fill in a 3. 2 times 3 is 6. I cannot fill in a 3 here because there's not a variable. So it would end up being 2. 6 and 2 do not match, so it's not differentiable. Okay, so it's continuous if you fill it into the original and they match. It's differentiable if you fill it into the derivative and it matches. Okay, let's do one more. You want to know, is it continuous at 1? That means you fill a 1 into each value. 3 times 1 squared minus 4. 1 squared is 1. 1 times 3 is 3. 3 minus 4 is negative 1. If I fill a 1 in here, 1 squared minus 5. 1 squared is 1. 1 minus 5 is negative 4. It is not continuous. There is a space there, so you will not be able to trace over because one piece, when at the x value of 1, the y value is at a negative 1. At the other piece, when the x value is a 1, the y value is at a negative 4. So you would definitely have to pick up the pencil. Okay, differentiable, find the derivative. Here, 2 times 3 is 6. You have the x, reduce the exponent, so the derivative is 6x. Here, bring the 2 forward. You still have the x. I had 2 x's, reduce it so it's down to 1. So you take the 2 derivatives, fill in a 1. 6 times 1 is 6. 2 times 1 is 2. These do not match. So this is also not differentiable, meaning if you graphed it, you could not draw a tangent line at negative 1. Okay, one more thing is just to really hammer home that because when you're doing these types of problems, you're saying that you're approaching a value. It's not saying that it equals that exact value. So you are allowed to simplify before, okay? So it says the functions below are defined for all values except for 1. If it's possible, define that function at that point in a way that makes it continuous, meaning simplify before to see if you can go ahead and cancel the issue. So if I want to go ahead and put a 4 in here, if you're trying to find the limit as x approaches 4, I can't fill a 4 in right there because 4 minus 4 is 0. So what you're allowed to do is simplify it. Factor the top. I have 3 terms. What multiplies to negative 12 and adds to a negative 1? Well, that's negative 4 and positive 3. Negative 4 times 3 is negative 12. Negative 4 plus 3 is negative 1. The bottom is x minus 4. I can go ahead and simplify that. I can cross off those 2 factors. So what I really have is find the limit as x approaches 4 of what's remaining, x plus 3. So go ahead and fill the 4 in now. 4 plus 3 is 7. I know some of you kind of struggled with that idea, so I wanted to make sure we had a few more of these, okay? I cannot put a 0 in there. So technically they're saying find the limit as x approaches 0. I can't put a 0 in there because the bottom would be 0. Try to factor it and see if we can do anything. On the top, I can take out an x. So I'd have x cubed plus 3x minus 5. The bottom is x cubed. Well, I can cross off 1x here and 1x there. There are no 2 numbers that multiply to negative 5 and add to a 3. So I can't factor this any further. There's nothing else in common. Oh, plus I couldn't do multiply add anyway because that's a power of 3. Can I put a 0 in now? No. We simplified it first and it still doesn't work. That's when the limit does not exist. If you try to simplify it first and it still doesn't work, then the limit does not exist. Okay? Here's another one. This is saying find the limit as x approaches 3 because it's saying, hey, this doesn't work for 3. But if you're doing a limit, we can make it work, possibly. Top, I can factor. What are 2 numbers that multiply to negative 6 and add to a negative 1? Well, that's negative 3 and positive 2. Negative 3 times 2 is negative 6. Negative 3 plus 2 is a negative 1. The bottom is x minus 3. You can cancel those 2 groups. Now I can do this. I can find the limit as x approaches 3 of what I have remaining. It's x plus 2. Go ahead and replace that x with a 3. So it's 3 plus 2 equals 5. That, my friends, is 1.5. Here's the suggested assignment. I hope you had a great time today, and I'll talk to you soon. Bye.